a sphere, and if I have a ray coming into that sphere, or multiple rays, can I assume there's some direction that you come in that it gets the critical angle? And I think my answer is no. And this is the reason, because if here's the normal here, this is going to be refracted toward the normal. And because it's a sphere, and because we have, say, mirror symmetry with respect to this line, that means that the angle that this ray makes with the normal is the same as this angle here, which means that out here it gets appropriately refracted again away from the normal. In other words, this angle is the same as that angle is the same as that angle. The only way you can have a problem is if it's a glancing, say this sphere was not a perfect sphere, but it was wobbled like that, right? Then this angle could be too large, and there is no refracted angle that'll work. But because of the symmetry, if it goes in a sphere, it has to come out, I think. Now that's not to say there isn't some internal refraction, right? Just like the light can also reflect off the surface of the sphere, there's some fraction that doesn't get back out. And so each time you spawn two rays, but total internal reflection means that there's no ray that gets out. And that's not going to happen in the case of a sphere. If it got in, it got to be able to get out just by the mirror symmetry. Does it make sense?
Yeah. So also the entrance ray and the exit ray leave at the same data relative to the normal?
Yeah, because of the symmetry of this chord with respect to the plane perpendicular to that chord. But that's a special case for a sphere.
Right.
I don't think it'd be true for an ellipsoid, for example.
Right.
Or, for a wobbly sphere. Okay, so today I just want to finish up what I was talking about last time when I ran out of time, and then continue with another topic. So what I didn't talk about is the inclusion of interreflections. So to summarize from last time, we expressed L, I guess it was called L0. I have to look back in my notes here. What did I call it? Yeah, I'm going to go so far back I'm wasting time, but see if I've got the equation. L0 x, direction of theta, was approximated by the sum of I of Li Ti, and in the book they call this 0. So this is actually a function of the point x, but we can tabulate it. Sorry, the Ti is what's the function of x. This is the spherical harmonic basis coefficients for the environment at infinity. And these are the spherical harmonic basis functions for the visibility and the cosine term of the BRDF local to x. And what this represents is the integral of I guess I should say rho x over pi integral over the sphere of the cosine term, the normal at x, and the direction. And then we have the visibility. Because this is the BRDF, I took it out of the integral. The visibility from x to infinity in direction omega, d omega psi. And then rays that start from x and hit the object are contributing 0 to this integral. But what we want to do is say, here's the object, and here's a point x. And a ray starting from x in direction psi will hit another point, say y, which we've denoted by rx psi in the past, which is another point on the surface, and that point on the surface has its own L0 going out in this direction minus psi. And so we can do another pass where we gather this reflected ray. So if I let L1 x, right now it doesn't matter, I'm doing diffuse only, so we don't need the outgoing direction. L1x is rho, and rho could depend on position x, of a integral cosine of psi comma nx. I guess I had them in the reversed order here. And now we'll put L0 here at y going into minus psi. And that's actually 1 minus the visibility toward infinity. d psi or d omega psi, right? So this integral includes all the rays that don't hit the object, and this integral, I guess if I replace this y by this r x psi, represents all the balances that do come in. And now, if I use the previous solution, which I've called L0 here, we can think of this rho x over pi, the integral of cosine psi nx, and then replace this by the approximation Li times Ti0 at x times this 1 minus Vx psi. Actually, if this ray, this was at y. I should not call this x, right? This was at r x psi. And this only makes sense if the ray didn't hit something. Did hit something, which is 1 minus this v. Then we can include the second bounce. We'll have L0 for the first bounce and then L1 for the second bounce. And then similarly we can continue with L2 and L3. And this also has this part which depends on the environment at infinity that's illuminating it, and a part which doesn't. So basically we can consider this integral as a product of these things, and we can express these things for each I in a series, right? So this is going to be rho x over pi times the how can I write it? Li Ti prime at x. Ti sub 1 of x, right? We want to do the same kind of sum as here, except we want to include the geometry of the first bounce in this factor here. So what that means is this is the integral of this kind of product, and so we have to let Ti sub 1 of x is the projection of this integral, this part of the integral on the basis functions. So that's integral omega x of the factors involved, Ti0 at r x psi times cosine psi and x times that 1 minus v, which basically says we're integrating only over the solid angle part where this ray actually, from x, actually hits a part of the surface rather than gets out toward infinity. You know, where we're only integrating any case over the hemisphere above x. And so we can express this approximately as a sum. Basically, how did we compute this TI0, or for that matter, the LI? We picked a predetermined collection of ray directions, and we, using the recursive algorithm for computing the spherical harmonics, for each I, we computed the spherical harmonics evaluated at that direction. And then to compute these I, this one, we multiplied those spherical harmonic weights. For a fixed I, we multiplied those weights by the environment at infinity and added them all up to get the integral form for how you get a spherical harmonic coefficient. And similarly for this guy. So we're going to do the same thing here, but we're only going to sum over directions k, where this ray in direction, say, psi k, starting at x, ray starting at x in direction psi k hits the object. Say at y. And then we're going to sum TI0 at that y to get this point times this weight, cosine psi nx. This is the thing we're evaluating times the basis function in that direction when we're adding it up to get. And, you know, if the directions don't have equal weights, maybe they have their specific solid angle for each direction is one of the options I talked about last time. So this is the formula for this. And basically, if you know the geometry at this point, how much of the environment it sees, you can compute this effect. And similarly, for two bounces, we can compute TI2 at each point in terms of TI1 at other points y. This y is, we can call it y. This yk is where the ray from x in that particular direction hits the object. And so we can build up as many bounces as we want. And because the contribution of each bounce has this reflectivity in it, and this is never bigger than a third or 1 over pi or whatever it is, and that means eventually, you know, the series will converge. And so basically we'll set Ti of x equals the sum over the number of bounces until we think it's conversion of Ti with that bounce of x, where b is one of these superscripts here. And that means we can get the contributions from all these bounces by a formula like this. And that means that our precomputed radiance transport can include inner reflections. Still, by precomputing some things that depend only on the geometry, and then later being able to add an arbitrary environment, rotate the object in the environment or the environment around the object, and stuff like that. Okay, so as I said last time, but I won't bother with today because I want to talk about something else. There is a further generalization. Instead of using a dot product here with two vectors, or I guess this is the general one, I didn't, you know, basically the actual L is going to be the sum over I of environment times this final I with no superscript on it, which has gotten all the bounces, we can find matrices, here, a matrix instead of a vector, which will actually get the dependence on the reflected energy as an extra variable, and then use that to get glossy reflections. But I'm not going to go into detail on that, because what I want to do is go into the paper, Hierarchical Radiosity. So that's going back to the framework where we had these set of linear equations we were solving with form factors as their coefficients. And this is a paper, SIGGRAPH 1991 by Saltzman. I'm not sure about that T. Hanrahan and Operley. And the reference that I used to prepare this lecture is this book, Radiosity and Realistic Image Synthesis by Cohn and Wallace. And that has it explained a little better than in this paper, but this is where it was first published. And the idea is we're going to take big polygons, like only one polygon for each wall and the floor and the blackboard, even though there's shadows and stuff on it, as the initial description in terms of patches, they call them. And we're going to think of dividing these polygons in, say, an octtree method, where you divide each octtree node, if necessary, into 4 smaller pieces. Or they could be triangles. You can divide each triangle in 4 by making 4 triangles using the midpoints of the edges. In any case, if you thought of dividing all the possible polygons in the scene up to some smallest area, say divide polygon by quarters recursively until each area is less than some area threshold, A sub epsilon. Okay, if you did that and get n small pieces, the smallest leaf octtree nodes are called elements. And then there would be big O of n squared form factors, or I say non-zero. That's because if each polygon is flat, the subpieces of the same polygon aren't going to see each other in the form factor. They'll have 0 solid angle if I took 2 separate polygons on the plane of the blackboard. But you can imagine, except for that case, there's still O(n) squared, where n squared is the size of the matrix. Some of those terms are 0, and most of them are non-zero. So it's actually omega of n squared, right? Usually people, theoretically speaking, it's a, say 5/6 of n squared, because only maybe 1/6 of the walls are hitting the same wall, something like that. So it's actually a lower bound. But if you divide adaptively, can get only O of n interactions. I call it an interaction where there's non-zero form factor. Interactions. And the idea is you're going to have an interaction between a given octtree node and a collection of other patches. But for the area of that node, there may be some other patches for which you have to subdivide that octtree node into smaller pieces. And the example that Hanrahan gives is if you have a polygon on the wall, say, and a polygon on the floor. And you think of dividing these into equal pieces, right? And so we're going to look at this quadtree nodes, and we're going to say, in terms of which interactions between these nodes and these nodes are well enough estimated by the form factor of just the flux between this one and each of those. And if you make an error threshold, if that error threshold is large enough, you'll say this interaction is okay, this interaction is okay, this interaction is okay, and this interaction is okay. But now if you look at one of these pieces of the floor that's right next to the wall, this is too close to this element, right? This is almost half the solid angle from here. So this is interacting only with this one, and that one, not with this one. And that means for the purposes of to see how these two interact, we have to subdivide. So now we'll subdivide this one into 4 quarters, and we'll subdivide this one into 4 quarters. And now if we say take this guy here, this is far enough from each of those 4 quarters to make an interaction. But if we take this one is too close to this one, and this one can only go to these 3 quarters, but not to this one. And so we'll have to subdivide these again and get a similar picture and so forth. We'll eventually have to stop. We can't be subdividing everywhere because we'll get patches that are too small, smaller than this area threshold. So eventually we're going to stop. But we'll have all these extra elements only near the wall. So any given one of these will only interact with, some collection of these bigger ones, not, a much, much smaller one. And that's the trick. Okay, so how are we going to organize this effectively? And that's where that radiosity book gives more detail than the original paper, because they actually give pseudocode, which the paper doesn't. And I think in this case pseudocode will help. So I'm going to copy as much of the pseudocode as I have time for on the board. So we have a quad node. And what it has is gathering radiosity, which is the radiosity that you're trying to build. And it has a shooting radiosity, which is the radiosity that will be gathered to other patches, which is complete after you add on not only the direct interactions, but the interactions with the children. So this is determined at the end of the path and then incrementally gathered into here with the links directly from the patch and from its children. And we'll have an emission we'll have an area. We'll have reflectivity. And that's useful because we could have textures where different parts of the wall had different colors painted on them or something, but everything else was just on the wall plane. And then we'll have children. In the original paper, they listed them northeast, northwest, southeast, southwest. In the book, they just say it's a list of. So this is a pointer to the head of this list of pointers to quad nodes. And then we have a link node. Link, which is one of these lines I've been drawing, which is going to have a place where it's gathering from and a node that gathering to and a node that is gathering from. And so this is just the first gathering link. So this is also a pointer to a list because it's a list of all the different nodes that P is going to gather from. And let me put it on here. Well, I guess I got more room here if I make this perspective. Take the bottom of this thing off so the perspective isn't quite as dramatic there. Struct link node. So it's got a quad node pointer P. That's the gathering node. Where you're pulling the radiance in across the link. And it's got a quad node Q, which is the shooting node. It's got a form factor. And then, because this is, we had over there a list of gathering nodes, we have to have a next. So that's a link node struct link node star next for that list. Okay, so what I'm going to do is tell you how you decide when to divide. And that's called an oracle. Somehow this oracle's got to predict whether to divide or not. And the oracle that the original paper proposed two different oracles. And the simplest one is Oracle 1, which we have a gathering node and the node that it's linked to, and we have some threshold. Basically, we're going to say, yes, we should link them if the error from the link in the form factor, say, is less than the threshold. And the most brute force method is to say, well, just if the form factor itself is less than the threshold, then the error probably will be, because the error is probably not going to be 100%. So, first of all, if P's area is less than the threshold and Q's area is less than the threshold, then we don't want to be dividing anymore. Like, we don't want to divide infinitely into those corners. So we'll return 0. Return. Because 0 is false. We don't want to subdivide. We're going to say when to subdivide. And now we'll say if the estimated form factor FPQ is less than this threshold, return 0, else return 1. So this estimated form factor is something you have to test really quickly. And so what they use is, if here is P and here is Q, a complicated polygon in general, they're just going to find the differential form factor of this polygon to this point. So you can either use the analytic formula that I gave you using that Nusselt analog to get the finite area to differential area form factor, or you can just, circumscribe a disk around this polygon in the plane of the polygon, or if you have a curved surface that you're parametrizing, that you're going to subdivide the parameter space by P and Q, say for a Bezier patch or a piece of a cylinder. You might want to put a sphere around the part and then, look at the disk, which is the in the tangent to the sphere. And then there's a simple, where this cone hits the sphere, you can get this disk. And then there's a even simpler analytic formula for disk to local point form factor. So that's all you use. You don't worry about occlusion or anything, because this is a very conservative thing, right? The whole form factor is less than epsilon. The error that you got by not doing the occlusion right is going to be less than that also. Later on, I'll give you a somewhat more sophisticated one. So now I want to give you refining, calling this oracle. So I forgot to specify my data types there, but since I'm now copying again on my notes, quad node, star P, quad node, star Q, and float. The minimum error. Actually, this looks like an epsilon instead of an E, I think, in the book I'm copying this from. So basically, if the oracle P, Q, Q with this error threshold is true, that means we should link these nodes. So link P and Q. Right? What that means, allocate and create this data structure. We put P and Q into it, and we compute the form factor and insert it into the linked list for that node P. And the way we compute the form factor is by ray tracing. Remember when I was talking about the shooting method, I said if you have two patches here, let me put my two patches here. We can think of taking jittered subdivisions of each patch. Take points in these and in those, and join them all and see which rays are occluded and which aren't occluded, and add the differential area to the point here. With a couple of cosine factors and a radius squared. Add them all together and you get an estimate of the form factor. Sort of a Monte Carlo estimate of that double integral over both areas. So you do that by ray tracing, but it's not worth doing it here because you might decide not to link. But you'll have to do it here when you build the link. Else, we're going to have to subdivide either. So if that oracle says, yes, we have to subdivide, we have to decide which of these to subdivide. And the easiest thing is to subdivide the one with the larger area, right? Because the relative form factor effect is going to be depending more on these areas. You could have something more sophisticated with the cosines, but the simplest is that. So if P, and in fact, I think the original paper actually looks at the form factors of the subpieces. But I'm just going to say, no, I think this is equivalent to what they do. If P area is greater than Q's area, then call this recursively, refine. Well, no, I have to do for each child, right? I have to call it recursively. For each child R of P, the one we want to subdivide, we're going to refine RQ, which means either compute form factors or for the sub pieces, or perhaps even refine some of them further, like I did. For some of those children, it took a third generation. Else, this should have been an if, and here's the else, refine the other one. For each child R of Q, that should have been an of, I was always thinking ahead of the letter I'm saying rather than the letter I'm writing. So now we're going to go from P to one of the subchildren of Q. Right, so basically we're going to do the process I was doing on the board about, if this oracle fails, then we have to divide this, and maybe this whole patch, even the quarters fail with respect to this one, so we'll end up dividing this one too, and then finally we'll add the links I drew here, except for this one, which will require further recursive refining and so forth. And so now we've refined, so we've done a sort of a top-down. We haven't drawn all these huge number n of minimal-sized little elements and then tried to see how we can amalgamate them by, computing the form factors and seeing what the error would be. We're going from top down, and so we're not even subdividing when we don't need to. So then, once we've done this and we've got these form factors, then we have to do iterations which are going to shoot or gather the energy. And so this code solve system has a loop which says while not converge, just like any of these other methods do, which are iterative solutions of the linear equations. But the things we can't just solve directly because we don't have a single set of linear equations. We don't even have a single set of single radiosities on each quadtree node because some of the radiosities are represented on the children. So we're going to have to say for all polygons, these are the initial polygons in the initial model P, do gather radiosity rad P. So I'll show you how that routine works, and for all polygons P, we're going to pull rad P. So I'll write these out in detail, but what this does is basically gathers the links to P that are there, whatever level in the quadtree it is, and then recursively calls the same routine for all the children of P to get their contributions from the link, and sort of adds them all up so that the ones at the lowest level get all the energy added on. That's what this push-pull does. And then once the lowest energy has the complete radiosity, then you average it up to the bigger elements. So then every element ends up with its correct shooting radiosity for the next step. So the gather radiosity, let's see, if I put this thing here, I might have room for this on one line on this board. Okay, for a quad node pointer P, says you start out by setting P's radiosity gather to 0. Turns out that for something like a texture, it's better, or a stained glass window, it's better to get the emission at the lowest level rather than assume the emission is constant on a polygon. So we'll add that at the bottom of the hierarchy, but for each gathering link of P, so that means P has a pointer to the first gathering link that one of these lines pulling into P, and they each have pointers to the next, unless it's null. And that's how we figure out what these links are, and now we can increment this BG by P's reflectivity times the link's form factor, right? Because each link has a form factor to go to Q, and then that LQ has a shooting radiosity. That is the radiosity that was accumulated in the previous pass. And you add that on, and you're doing basically that sum that you're doing like for the gather part of the radiosity equations. But note that we have, because we haven't got them all accumulated correctly until the end of gathering all the children, we can't get the advantage of the Gauss-Seidel iteration of getting them updated as we go along. We have to gather them all and then update them all, including all their children, to get the next generation, next iteration shooting. So it's really corresponding to what I call the Jacobi iteration, where you have a vector of things and you compute the new vector in terms of the old vector and then rewrite the vector that's going to be used in the next iteration. So you're not, gathering previously gathered stuff partially from the same iteration. So in that case, it's not Gauss-Seidel advantage. And there's no advantage in doing it as shooting and picking the one with the most, biggest form factor to go next, or the biggest flux to shoot next, because this sort of scheme for this oracle is sort of making the flux along each link all equal. So there's no advantage in doing certain ones out of order. And so then we just have to do it for each child. Of P, following its list of children, do the same thing. Gather rad, what do I say, child R of R. So that just guarantees that as you're going down this hierarchy, starting from an initial big polygon, you'll do the gather for all the pieces of the hierarchy. Because you start it with each polygon Q. We're calling this for every polygon. And for every polygon, we're recursively calling it for its children. So we've now gathered across all the links to each child. And then we have to do this push-pull, which is the idea, before I erase this, if we really want to know the flux that's coming into P in order to shoot it out to the next one, we've got to, actually, because I already multiplied it by the rho, I'm doing already the BRDF part of it, and it's already the outgoing radiosity contribution now, rather than the irradiance, because I've already multiplied it by this rho, which is like the BRDF. We have to get on this patch here, these extra links that we needed for its children, because part of it wasn't gathered at this pass. This part is only gathered at the next pass. So we have to add the flux we got here to whatever extra flux we're getting here. And then we'll get the flux at the elements, the smallest pieces, and then once we get the total flux on each of the smallest piece and also add on its emission, then we'll have to average those radiosities to get the radiosity all the way up the tree. So that's what this push-pull is doing. Pushing down to the lowest element while adding, and then pulling up to the root of this sort of octtree hierarchy on each original polygon by averaging radiosities. So float, push, pull. Did I have the word radiosity in my call here? Push, pull, rad. And that's from 2 patches. So this is quad node P. And it's going to be a float B down, which is the radiosity that came from the parents. Because we're going to be adding that up as we work our way down the hierarchy. So if P is a leaf, namely its pointer here is null, it's got no children, then B up, so I have 2 floats here that I need. B up, which is what you'll send back up the hierarchy when you return, and B temp. So what you're going to return up the hierarchy is the element's emission, but because I said we store emission at the finest level for things like textures, plus its own gathered radiosity that we got from this call here, plus the B down that was passed from the parent. Okay, else we initialize the B up to be 0 and then add on the radiosity from each of its children. So B temp equals push, pull, rad. Okay, so I missed my loop for my children, so I started writing it here. Let me put on the same line B up equals 0, and for each child R of P, we'll push-pull radiosity R, but what we're going to give R for its down is the down it had plus the P. P had a gather link itself, right? So it's getting from its parents, it got B down, it's got this own gathered radiosity, and it's saying that's the initial radiosity that's going down to its children. So when this returns, it's done this at all the leaves, and now it's gonna finish going up. So basically what we're going to return at the end of this thing, we're going to take the shooting to be this B up, which we're adding here. I haven't told you how yet. And then we're going to return B up. And so what we want to do is, in our case, if we're actually dividing things into quarters, by taking the average, we take a quarter of each. But if for some reason, say this quarter was missing or had a hunk out of it, right? Because we had this irregular shape that we were trying to, like the doors are missing from that wall, and so the things didn't have an error. In general, we're going to say B up equals this B temp. This plus equals, right, because we're adding it on to for each one. The ratio of R's area to the parent's area. So this would be 1/4 unless it had pieces out of it. You could think of adding all these numerators as getting the total radiosity times area as flux. And then flux divided by the total area is radiosity. And so it's a sort of a weighted average if they're unequal. And then by the time these all the way go up, then each patch has its shooting radiosity now updated to get all the stuff from its children and passes that average on up to its parents. And now they all have the accumulated radiosity from all of their children. And then that's good enough for the next iteration. So my time is up, but let me tell you one modification for the oracle, which is instead of doing this test, if you're iterating through, initially you're going to have only this emission, right? Because these things haven't gathered yet. And as you continue, you're going to build up more radiosity, and it's if you make a threshold, which is radiosity times area times form factor, then what you're really doing is saying if the flux is on a link is bigger than a threshold, we subdivide. So this if, where we're going to return 0, if it's less than this threshold, is going to say if Q's current BS times its current area times the links FPQ that you got so far is less than this flux limit, then we'll subdivide. So now if something has a bigger area, it'll be subdivided, and if along that link, more total flux is coming, it'll be subdivided. So now we're sort of equalizing the flux on the links. And as more bounces come from the lights on the wall, we'll end up subdividing the wall if necessary. And so that's a better oracle. They call oracle 2, and that ends up maybe not subdividing as finely, because dark areas won't need to be subdivided as much. You can't see them, and they're not going to accumulate as much flux to other areas. So you may end up with even less links than you would just with this form factor based estimate. So that's it for my lecture. Sorry for the extra minute and a half, and I'll see you all on Friday, hopefully with interesting projects to show. So be prepared to either bring a laptop or a thumb drive that we can use this projector on.